Hello, I'm Patty Simpson with Simpson Math. Let's multiply and divide fractions. So when we multiply fractions, we simply multiply straight across. The numerator times the numerator and the denominator times the denominator. So for instance, here we have 1/2 times 2/5. We are just going to multiply the 1 times the 2 and the 2 times the 5. So we're just going to multiply straight across. Now, we can multiply that straight across and then reduce so that we have on top 2 over 10. Notice that there's a 2 on top and a 2 on bottom. A factor goes into both of those. So if I divide the top by 2 and I divide the bottom by 2, I end up with 1/5. What I like to do when I'm multiplying fractions is instead of waiting till the end to reduce, I like to reduce along the way to make it a little easier on myself. Notice that that factor of 2 that was in 2 and 10, I can see that factor here. There's a factor of 2 on top and a factor of 2 on bottom. If I go ahead and simplify that here, I also end up with 1/5. So when we multiply fractions, we simply multiply straight across. But if we can reduce or simplify first, it might make things easier for ourselves in the long run. Here's another example. Let's do 2/3 times 9/16. And again, literally what we're going to do is just multiply straight across so that I have 2 times 9 over 3 times 16. And I could just simply do that multiplication so that I have 18 over 48. And then I could reduce that fraction. Well, there's a multiple of, or a factor of 6 that goes into 18 and 6 goes into 48. So I could divide the top and the bottom by 6 to get 3, and 6 goes in there 8 times. Or what I could do is I could recognize earlier that when I have that 2 times 9 over 3 times 16, I could recognize at that point that a 3 is in the bottom and is in the top. Notice that 3 goes into 9 3 times. And notice that 2 is a factor on top and 2 is a factor on bottom. So I could reduce that here so that 2 goes into 2 1 time and 2 goes into 16 8 times. Then when I multiply straight across, I still end up with that 3/8. So either way, I end up with 3/8. Here's one last example of that. In it, I'm just going to simply do my simplification or reduction first. These numbers are large. Trying to multiply those out might be tough. So instead, if I can make it simpler on myself to begin with, I think I'd like to do that. So for instance, I see that 7 goes into 14 and 7 goes into 35. So I'm going to divide the top and the bottom by 7. 7 goes in here 2 times, and 7 goes into 35 5 times. I also notice that 3 goes into 9 and 3 goes into 15. So I'm going to go ahead and simplify by 3 on top and bottom as well. So 3 goes in there 3 times, and 3 goes in here 5 times. There isn't a factor of 2 on the bottom. There's not another factor of 3, so I know I've simplified that down. Now I'm just going to simply multiply across. So 2 times 3 gives me 6, and 5 times 5 gives me 25. So 14/15 times 9/35 is equal to 6/25. Now, when we divide fractions, we're going to just multiply it by the reciprocal. In other words, we're going to keep this first fraction the way it is. We're going to change our sign from division to multiplication, and we're going to flip him That's what the reciprocal is. It takes this and it flips it. So we're going to multiply by that reciprocal. We're going to keep, change, flip. It's almost KFC, but not quite. So I'm going to do exactly that. I'm going to keep my first one. I'm going to change my sign from division to multiplication. And then I'm going to flip the second one. Now we're just back to multiplication. Right back to where we were before, where we're just going to multiply straight across. Top times top, bottom times bottom. And if we can simplify to begin with, let's go ahead and do that. So for instance, here I see a 4 divided by 2, which equals 2. So on top, I end up with 2, and on bottom, I end up with 3. So 1/2 divided by 3/4 gives me 2/3. I'm going to do the same thing here. I'm going to keep my first one, 75/88. I'm going to change my sign from division to multiplication. And then I'm going to flip my second one. So I have 44/25. Now I'm just going to multiply straight across. But if I can find something to simplify, I'm going to do that first. So for instance, 25 goes into 75 3 times. And 44 goes into 88 2 times. So when I multiply straight across, I end up with 3/2. So 75/88 divided by 25/44 is equal to 3/2. So multiplication, multiply straight across. Division of fractions, you keep the first one, change your sign to multiplication, and flip it, or multiply by the reciprocal. Let's add and subtract fractions. In order to add and subtract fractions, we need a common denominator. In other words, the bottoms of our fractions must be the same in order for us to add or subtract the fractions. So we're going to first find a common denominator each time. Then we'll find an equivalent fraction. So we'll make sure that we change our fraction into that denominator, and yet they'll still be equal fractions. And then we'll add and subtract the numerators of our fractions. So let's do a few examples. Here, I have 1/7 plus 3/7. Notice that the denominators are already the same. It's already cut into sevenths. So I can just simply add our numerators here. 1/7 plus 3/7 is equal to 4/7. We just add the numerators once our denominators are the same. Now, we're going to add 1/3 plus 1/6. Their denominators are not the same. 3 and 6 are not the same. We need to make them into the same number. And in order to do that, we have to find a number, a multiple of 3, that is also a multiple of 6. In other words, if I count by 3s, 3, 6, 9, 12, 15, I'm looking for a number that is a multiple of 3 that is also a multiple of 6. So if I count by 6s, 6, 12, 15, 18, some number that's the same. Notice that 6 is the same. They're both a multiple of 3 and a multiple of 6. We could also use 12 because 12 is a multiple of 6 and a multiple of 3. We could also use 15 because 15 is not a multiple of 6. So no, we can't use 15. We can use 6, 12, we could use 18 because that's also a multiple of 3. So you're looking for a multiple of 3 and a multiple of 6. But we would really like to use the smallest of those or the least common multiple. So I'm going to use 6 as my common denominator. So we've decided what our common denominator is going to be. We found that common denominator. The next step is to create equivalent fractions. In other words, I want to create a fraction that is the same as 1/3, but has that 6 as a denominator. So as I think about it, I want this 1/3 to be equal to something 6. Well, in order to do that, I would have to multiply my denominator by 2. 3 times 2 gives me 6. Therefore, I'm going to multiply my numerator by 2 as well. 1 times 2 is 2. Notice that this 2 over 2 is just a fancy way of saying 1. And when I multiply a number by 1, I don't change the number. So 1/3 is the same as 2/6. These two numbers are the same thing. If I eat 1/3 of the pizza, that's the same thing as eating 2/6 of the pizza. This is Michael in his bathing suit, and this is Michael in his tuxedo. They're the same guy, they just look a little different. I'm going to add that. Well, notice that my 1/6 already has a 6 in the denominator. I don't have to change him. He's already dressed that way. So I'm just going to leave him as 1/6. Now, once I have their denominators the same, I can just add their numerators. So 1/3 plus 1/6 is equal to 3/6. I'm going to simplify that. In other words, I'm going to divide the top and the bottom by another fancy 1, 3 over 3, so that that's just equal to 1/2. So it turns out that 1/3 plus 1/6 is actually equal to 1/2. Here, let's add 4/5 plus 1/4. Again, I'm going to count by 5s, 5, 10, 15, 20, and I'm going to count by 4s, 4, 8, 12, 16, 20, and I'm going to look for a multiple that is a multiple of 5 and a multiple of 4. Another way to find a common denominator is just to multiply these two together. So 5 times 4 gives me 20. When I counted by 5s, I got to 20. When I counted by 4s, I got to 20. So I could just make both of these denominators be 20. Sometimes that's not the least common denominator, but it's always a common denominator. It might not be the least one, but it is a way to get a common denominator. Now I'm going to make an equivalent fraction. I want this still to be equal to 4/5, but with a 20 in the denominator. So what I did was I multiplied this 5 by 4 to get to 20. I'm going to do the same thing on top because I'm just multiplying by a fancy 1. So 4 times 4 is 16. Here, to get that 4 to 20, I multiplied by 5. So I multiply the top by 5. 1 times 5 is 5. Once their denominators are the same, I can add the numerators. So 16 plus 5 is 21 20ths. That's more than one whole thing. 4/5 plus 1/4 is equal to 1 and 1/20. Now let's do some subtraction. We do subtraction the same way. The first thing we need when we're subtracting is a common denominator. So I'm going to find a common denominator. I can count by 3s, I can count by 5s, or I can simply multiply these two together. 3 times 5 gives me 15. So 15 is a multiple of both of those. Then what did I multiply 3 by to get to 15? I multiplied it by 5. So 5 times 2 is 10. I multiplied this 5 by 3 to get to 15. So I have to multiply the top by 3. So that's 9. So 10 15ths minus 9 15ths. Again, once I have that common denominator, I simply subtract the numerators. So 1/15. Here I have 8 and 12. I could just multiply it together and say that my denominator is 96 because 96 is a common denominator. Or I could count by 8s. I'm going to do it a little bit different this time just to show you another method for finding the common denominator. Notice that this 8 and that 12 both have a 4 as a factor. So 4 times, if I divide that into 8, it goes in there 2 times. 4 times 2 is 8. If I divide that into 12, it goes in there 3 times. So 4 is a common factor of both of those. I'm going to take and multiply these factors together to find its least common denominator. So 4 times 2 is 8 times 3 is 24. Now let's see if that makes sense. 8, 16, 24 is a multiple of 8. What about 12? 12, 24. Sure enough, 24 is also a multiple of 12. So 24 is our least common denominator. I'm going to write both of these with 24 in my denominator. So to get there, I multiplied this 8 by the 3 to get to 24. 3 times 5 is 15. I multiplied the 12 by the 2. So 2. Once I have that common denominator, 5/8 is the same as 15/24. And 1/12 is the same as 2/24. Once I have the common denominator, I just simply subtract in the numerator position so that it's 13/24. So when we're adding and subtracting fractions, a little more work is done than multiplying and dividing fractions, because when we add and subtract, we must first have a common denominator. Then we find that equivalent fraction, and then we can add or subtract those numerators. Let's look at probability rules. So first, we have this spinner here, and we're just going to find some probabilities. Let's find the probability of an even number, of spinning an even number. Remember that to find the probability, what we do is we take the total number of outcomes. In this case, there are 1, 2, 3, 4, 5, 6, 7, 8 different pieces. And we look at the number of those events. So here, evens. There are 1, 2, 3, 4 even numbers. So the probability we spin and hit an even is 1/2, or 4 out of 8. Now let's look at the probability of hitting a 3. If we spin that spinner again, we have, again, 8 pieces are my total, and there's 1 3 on my spinner. So the probability I get a 3 is 1 out of 8. Now let's put those together. I'm just going to spin my spinner one time, but if I spin my spinner one time, what's the probability that I get an even or a 3? Well, we know it's the same idea, where we have that 8 on the bottom, and then we know there are 4 evens and 1 3, so there are a total of 5 things that I could hit that are even or 3. So it's 5 out of 8. 1, 2, 3, 4, 5 chances out of the 8 chances. Notice that what we did was we took the 4 out of 8 and the 1 out of 8, and we just added those together to get the 5 out of 8. So when we had this or in there, we just added our probabilities to get the new probability of or, of both of them. Let's try that again. Now let's look at the probability of even. Oh, we did that before. It was 4 out of 8, or 1/2. Then we found the probability of pink. Well, there are 2 out of the 8. 2 out of the 8, or 1/4. What's the probability that I get an even or a pink? Well, if I did like I did before, where I added those together, we would say 4 8s plus 2 8s, which equals 6 8s. Let's see if I have 6 out of 8 chances to get an even or a pink. Let's count them. 1, 2, that's even. 3, that's even and pink. 4, 5. So there are actually only 5 out of 8 chances. And that's because when we added these together, we actually added this pink 4 in both categories. But he is only one spot on there that I'm spinning. So I actually need to subtract off that overlap. So that it just ends up being 5 out of 8 chances. So when I have this or, and the two things do not overlap, we say that they're mutually exclusive. When they're mutually exclusive, we can just add the probabilities together. But when we have this or, and they are not mutually exclusive, when they overlap, we can add the two probabilities together, but we have to subtract off any overlap. Like in this case, the pink 4 is in both categories. So I counted him in both categories, I have to subtract him off then. Let's try some more of these. So what's the probability I get an 8? Well, there's 1 8 out of 8 pieces. What's the probability I get a green? Well, there are 1, 2, 3 greens out of the 8 pieces. What's the probability I get an 8 or a green? Well, again, 1, 2, 3, 4 different places I can land. 4 out of the 8. Or these are mutually exclusive. In other words, they don't overlap. My green ones are not an 8, and my 8 is not green. Since they are mutually exclusive, I can just add their probabilities together. 4 8s or 1/2. Let's try one more. What's the probability of even? We've seen that several times. It's 4 out of 8 or 1/2. What's the probability of green? We saw that earlier, 3 8s. What's the probability we get an even or a green? Well, an even would be the 2, the 4, the 6, or the 8, but that 2 is also green, and so is the 6. So in this case, I'm only going to add 1 more to those evens. There's 1 additional green guy. So they are not mutually exclusive. So I'm going to add my probabilities of the two, but then I have to subtract off the overlap. In this case, there are 2 greens that are even. There are 2 of them that I'm counting in both places. So we have 7 minus 2 gives me 5 8s is my probability. So the rule is when I am adding, when I have the probability of 2 events, the probability of A or B, what we're going to do is we're going to add the probability of the first one plus the probability of the second one minus any overlap between them. So add the 2 probabilities and subtract the overlap. If they happen to be mutually exclusive, if they don't overlap, then we don't have to worry about the back part. But that's only if they are mutually exclusive. So anytime we see that or think of the or, we're going to add and subtract any overlap. So that's one of the probability rules. So we just looked at the probability rule for when we have or. When we're doing one stage of an experiment and we're looking for 2 different things with an or in between them, and we add those probabilities. And if there's an overlap, we subtract the overlap. But what about if we're doing 2 different stages of an experiment? For instance, I'm going to spin this spinner not just once, but twice. And I want to know what's the probability that I get an even and then I get another even. So instead of having that or in between, I have this word and in between. What's the probability then? Well, what we're going to do to help us figure this out is first, let's just draw that symmetric sample space to help us find the probability. We've used that symmetric sample space in the past to find the probability. So let's do it again. So on the first spinner, we know that our outcomes, our possible outcomes, are 1, 2, 3, 4, 5, 6, 7, and 8. And we know on the second spin that our outcomes are 1, 2, 3, 4, 5, 6, 7, and 8. So we can find all the possible outcomes by making this symmetric sample space, by making this chart to help us see our outcomes. So if I spin a 1 on the first spinner, I could spin a 1 on the second spinner. I could spin a 1 on the first spinner and a 2 on the second spinner. A 1 on the first spinner and a 3 on the second spinner. And I just continue to fill this in until I get all my different possibilities. So there's all the possibilities with spinning a 1 on the first spinner. Then I can do the same for spinning a 2 on the first spinner. So I'm going to finish filling in our symmetric sample space. So now I have the entire symmetric sample space, all the possible outcomes for spinning this spinner twice, where I could spin 1 through 8 on one spinner and 1 through 8 on the other spinner. And we want to know, what is that probability that I get an even and an even? Well, first of all, let's look at the total number of outcomes. And the way we do that is we just say, well, there are 8 rows this way and 8 columns that way. So if I were to count all of them, there would be a total of 64. 8 times 8 gives me 64. That's my denominator. Then to find out how many are even and even, I'm going to go through and look at all the ones that are even and even. So I'd have to get an even on my first spin. Well, that eliminates all of this row. That eliminates all of the 3 row. So none of those, and it eliminates my 5s, and it eliminates my 7s because those are all odd. So then it has to be within this row, and then it also has to be even on the second spin. So an even and an even, an even and an even, an even and an even, an even and an even. An even and an even, an even and an even. 4 and 6 are both even, 4 and 8 are even. 6 and 2, 6, 4, 6, 6, 6, 8. And then 8, 2, 8, 4, 8, 6, 8, 8. So you see we also eliminated down the 1s, the 3s, the 5s, and the 7s there. So how many total are even and even? Well, there's 1, 2, 3, 4 by 4 of them. So there's a total of 16 that are even and even. Now, how did we really go about getting that probability? Well, the probability that we got an even on one spin was 1, 2, 3, 4 out of 8. And on the second spin, the probability that I get an even on that second spin is again 1, 2, 3, 4 out of 8. So notice what we did with these numbers. In order to get to the 64, I multiplied 8 times 8 to get to the 64. And in order to get that 16, I really multiplied this 4 times that 4. 4 times 4 gave me the 16. So this and really was telling me to multiply those numbers. Or I could have simplified it. I could have said 4 eighths, and 4 eighths is 1/2 times 1/2, which is 16 goes into 16 one time, 16 goes into 64 4 times. 1/2 times 1/2 is 1/4. So that's the probability I get an even and an even. I used that symmetric sample space, but really all I did was multiply those probabilities. Let's look at spinning these 2 spinners. So here I have a spinner with green, red, and blue, and there I have a spinner with the numbers 1, 2, 3, and 4. I want to know what's the probability that I spin a red and a 2. Again, let's use that symmetric sample space to help us figure out that probability. Well, on the first one, I can get a red, a blue, or a green. And then on the second spinner, I could get a 1, a 2, a 3, or a 4. So if I look at all my possible outcomes, I could get a red 1, a red 2, a red 3, or a red 4. I could get a blue 1, a blue 2, a blue 3, a blue 4. I could get a green 1, a green 2, a green 3, or a green 4. Well, before we find the probability using that symmetric sample space, let's just look at the individual probabilities. What's the probability I get a red just on this spinner? Well, it's 1 piece out of a total of 3. So that's 1/3. I'm going to write it over here, 1/3. Then what's the probability that I get a 2 on this spinner? Well, it's 1 out of 4 pieces. So let's look at that symmetric sample space and see what the probability is that I get a red and a 2. Notice that there's a total of 12 outcomes. 3 times 4 gives me a total of 12 outcomes. So there are 12 different outcomes. And the way I got that is looking at the symmetric sample space. I have 3 rows, 4 columns, so I'm really multiplying that 3 times the 4. Then how many outcomes have a red and a 2? Well, red 2 only shows up in one spot. Or you can think of it as this multiplication. 1 times 1 gives me 1/12. So when I see that and, when I'm doing 2 stages of an experiment and looking for those 2 outcomes, I can really just multiply their probabilities together. So here, instead of drawing the symmetric sample space, let's just find the probability by using that multiplication. Draw 2 marbles with replacement. What's the probability of getting a red and then a blue? So we want the probability of getting a red and then a blue. Well, the probability I get a red, there are 3 reds in my urn here, or my jar, out of a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That and, now I know, just means to multiply. Then it says with replacement. So in other words, I took the marble red one out, I looked at it, I put it back in, all 10 of them are in there again. I'm going to now draw a marble out. What's the probability I get a blue? Well, there are 4 blues, again, out of that possible 10, because we put that red one back in. That makes them independent events. This spinner is independent of that spinner. This spinner, the first time, is independent of the second one. And both of these probabilities are independent of one another since I put the marble back in. So now I'm just going to simply multiply. 3 times 4 on top and 10 times 10 on bottom. You could just multiply those out. I always like to simplify before I multiply to make my numbers smaller. 3 doesn't go into anything in the denominator, but 4 and 10 both have a factor of 2. 2 goes into 4 2 times, 2 goes into 10 5 times. So now I've got 3 times, this 2 and that 10 also have a factor of 2. 2 goes into 10 5 times. So I have on top a 3, and I have on bottom 5 times 5, which is 25. Or maybe you just did 3 times 4 and got 12 over 10 times 10 was 100, and then you divided by 4 over 4, and you also got 3/25. So the probability I get a red and then a blue is 3 out of 25 times I would expect that to happen. So the rule here for and, when they're independent events, is I'm just going to take the probability of my first event. So if I have the probability of A and B, and they're independent, I do the probability of A times the probability of B to find the probability of both of them. Let's talk about conditional probability. So conditional probability is when I have some information, and because of that, my probability changes. So for instance, here, if I wanted to know what is the probability that I spin a 1 on this spinner, Well, that probability is there's 1 1 out of a total of 8 numbers, so it's 1 out of 8, or 1/8. But now I'm going to change this just a little bit. I'm going to give you a condition for this probability first. I'm going to spin the spinner and hide it from you. And then I'm going to tell you that the spinner's landed on an even number. So you know that it's landed on an even number. Now, what's the probability that it landed on a 1? Well, it can't have landed on a 1 if you know that it landed on an even number. So the probability that it landed on 1 was 0. So that is called conditional probability. We now have this condition that it landed first on an even number, and it changed our probability. It changed it from 1/8 to 0. Now I'm going to show you some notation, or how we write this probability when we have that condition. Here, we're still looking at the probability that it lands on a 1, but we're given, or we know, that it's actually on an even number. Well, the probability that it lands on a 1, given, that little line means given that it landed on an even number, was 0. So when we had this information, it changed our probability. It changed our probability from 1/8 to 0. And we call that conditional probability. Let's do some more conditional probability. Here I have a two-way table that shows the votes on a bill. It says, suppose that after a vote in the U.S. Senate on a proposed health bill, the following table shows the breakdown of votes by party. By the way, do you know how many U.S. senators there are? Each state has 2 senators. There's 50 states. So that means there's a total of 100 senators. Learn a little history in this stats class too. Okay, so here, let me just ask you some different probability questions just based upon that chart. For instance, if I asked you, what's the probability that we randomly choose a senator? We're just going to randomly choose one of the senators out. I want to know, what's the probability that they're a Democrat? Well, remember, the way we find probability is we take the total number of senators, in this case it's 100, and we find the number of Democrats, that is 45. So the probability that I randomly choose a senator from this group is 45 out of 100. Or maybe we simplify it, divide by 5 over 5, so we get 9/20. Or 45% is our chance of getting a Democrat. Okay, let me change it just a little bit. What's the probability that I get someone who votes in favor of the bill? A senator in favor of the bill. Again, total number of senators is 100. Total number of those who voted in favor was 42. So the probability that I get someone in favor of the bill is 42 out of 100, 42%. Or we could divide the top and bottom by 2 and get 21/50. Okay, now I'm going to make a condition on this. I'm going to make it a conditional probability. So that I ask you, what is the probability that they vote in favor given that we know they're a Democrat? So now in this case, I'm not looking at all the senators. Now I know that I'm only looking at those Democrats. For whatever reason, I'm standing outside the Democrat door, or I only have the pile of Democrat votes. And I want to know, what's the probability that I grab a vote that is in favor when it's only the Democrats? It changes my total number. Instead of looking at out of the whole 100, I'm now only looking at those Democrats. I'm only looking at the 45. So my probability now is the ones in favor that are also Democrats. So I'm only looking at these Democrats. So it's a total of 45. And then the ones that are in favor that are those Democrats are the 32. So it's 32 out of 45. So you see with the conditional probability, whatever my condition is becomes my denominator, and then the two together become my numerator. It has to be both of those is my numerator. And that is conditional probability. Let's use the idea of that conditional probability to help us solve this. Draw two marbles here without replacement. What's the probability of getting a red and then a blue? We learned earlier that this and, when I'm trying to get the probability of a red and then a blue, and then a blue, that and tells me I'm going to multiply. I have two different stages of this experiment, and then I need the probability of this one and the probability of that one, so I'm going to multiply those probabilities. So the probability of red is, well, there are 3 reds out of the total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 3 out of 10. And I'm going to multiply. But this second one is conditional on the first one being chosen. And because it's without replacement, I now have one of these reds in my hand. I didn't put it back in the urn this time. And so therefore, this probability of getting a blue has changed. Instead of being 4 out of 10, it is now 4 marbles, 4 blues out of 9. So it was on the condition that that red one was chosen first. But now I just multiply as I did before. So finding that probability when it was without replacement, my probability changed from what it was earlier. So now I just multiply. Again, when I multiply, instead of multiplying the numbers and then simplifying, I like to simplify first. So 3 goes into 9 3 times, and 4 and 10 both have a factor of 2. So 2 goes into 4 2 times, and 2 goes into 10 5 times. So on top, I just have 2, and on bottom, 5 times 3 is 15. So the probability of getting those 2, red and then blue, when it's without replacement, is 2 out of 15. Let's put these probability rules together now, and then do a few examples using those rules. First, when we have one experiment, one thing that we're pulling out, and we want to know if that this or that, where we have this or in between when we set it up. If they are mutually exclusive, in other words, they don't overlap, we just take the probability of the first one and add it to the probability of the second one. If they're not mutually exclusive, in other words, if there is some sort of overlap, if they can happen at the same time, then we take the probability of the first one plus the probability of the second one, and we subtract their intersection where they are overlapping. We subtract that probability where they overlap. Now we are going to use this addition when we're just pulling out one thing, or if we're just spinning a spinner one time, or rolling a dice once. Then we use this or when we have 2 events that we're looking for. The multiplication rule, though, is when in our head we think and. We have 2 separate stages of an experiment we're doing. We're spinning 2 spinners, or we're rolling 2 dice, or we're choosing 2 marbles. Then we're looking for the probability of an event and an event. When we have that and in there, then we're going to multiply. And if it's independent, if each one of those is independent, like spinning the spinners or flipping a coin or rolling a die, then if they're independent, we're just going to multiply the probability of the first event times the probability of the second event. If, however, they're dependent, if it's conditional upon the first thing, for instance, if it says without replacement, so there's that condition upon the first one, then we're going to take the probability of the first event and then the probability of the second event on the condition that the first event occurred. So there are your probability rules written up generically or in general. Let's do a few examples. A survey of college students found that 56% live in a dorm, 62% have a meal plan, and 42% do both. What's the probability that a randomly selected student either lives on campus or has a meal plan? Notice that we're only going to randomly select one student. So here I'm looking for the probability that they live in a dorm or they have a meal plan. So that or tells me that I'm just going to add those probabilities. So the probability that they're in a dorm is 56%. The probability that they're on a meal plan is 62%. Notice that if I add those up right now, I'm going to be over 100%. And we know that our probability has to be between 0 and 1. It has to be between 0 and 100%. So I can't have a probability that ends up over 100%. So what do I have to do here? Well, these are not mutually exclusive. They can be in a dorm and have a meal plan at the same time. So therefore, I need to subtract their overlap. And in this case, the overlap is the 42%. So now I just do some addition and some subtraction. So 62% minus 42% would give me 20%. 20% plus 56% is 76%. So 76%, the probability that I randomly choose a student that has a dorm or a meal plan would be 76%. Let's do another example. What's the probability that if we draw a card, put it back in the deck, and then draw another card, that we draw a queen and then a king? Notice that I'm doing two stages of an experiment. I'm going to pull out a card, and then I'm going to pull out another card. And it says with replacement, I'm putting it back in the deck. So each one of them is going to be independent of the other. So writing it in notation, I'm going to do the probability that I get a queen and then a king. So what's the probability I get a queen? We do need to know a little something about cards. If you don't know something about cards, you may want to go to the dollar store, buy a little dollar deck of cards and play some solitaire or play some Go Fish. Get familiar, sort your deck to find out how many suits there are and how many are in each one. You're going to need to know a little bit about cards. So go play some with some cards. Go play some Go Fish. So there are 52 cards in a deck. So my total number of cards I could draw from are 52. And there are 4 queens in the deck. So the probability I get a queen is 4 out of 52. This and tells me I'm going to multiply. Because I put the queen back in, there are again 52 cards in the deck. And there are also 4 kings in the deck. So it's 4 52s over 4 52nds. So I'm going to multiply those two together. I can reduce first. You could multiply straight across and then reduce, but that's going to give you a really big number. I like to reduce first. 4 goes into 52 13 times, and 4 goes into 4 1 time. I'm going to reduce this one as well, 1 over 13. So I end up with 1 over 169. So the probability that I get a queen and then a king, if I drew 169 times those 2 cards, putting it back in, I would expect 1 time for me to get a queen and then a king. 1 out of every 169 times is my probability. Let's do one more example. There are 17 men and 24 women in a club. 2 members are chosen to be on a committee. What's the probability of a male and then a female? Notice again that I'm choosing 2 things, just like I chose 2 cards or I spin 2 spinners. I'm choosing 2 things, 2 people out of this club. So when I get ready to write it, I'm going to use that and in between. And I want the probability of a male and then a female. So what's the probability? Well, the probability I get a male is 17 out of a total of, well, that's 30, 41. So out of a total of 41. And then the probability that I get a female, well, am I going to put that man back in? Do I still have 41 people in there? I don't think so. Instead, I'm going to have 40 people now because the man has already been chosen. So now there are only 40 people in the club. And then how many of those are female? Well, 24 of them are female. So my probability changed based upon that first one being chosen. So now I just do this multiplication. I'm going to simplify first again to make it a little easier. 41 is a prime number and so is 17. But 24 40ths then does simplify. 8 goes into both of those. 8 goes into 24 3 times. And 8 goes into 45 times. So now I do this multiplication and I end up with 51 over 5 times 41 is 205. So 51 out of 205 times is the probability that I get a male and then a female. So here it was without replacement. So we can use those probability rules to help us to solve these probability problems. Math made simple. It's some math. Thanks for watching.